I left off. I'd actually started off talking a little bit about the encoding of sequential information in the theta rhythm. So I want to continue to follow this idea that there's a mechanism of encoding and use of memory during sort of conscious active awareness that makes use of the fact that the theta rhythm can be used to synchronize activity between areas. And so again, we're going to talk about the theta rhythm during active, I refer to as sort of online behavior. And again, just remind you that the code, the theta code, is actually a sequential code that includes information linking together recent past with the near future. And this occurs repeatedly. And so you can imagine that if you're forming a code that actually can do kind of short term prediction, that you might make use of this in the course of normal behavioral decision making. And the structure that you think of when you think about kind of executive function decision making is the prefrontal cortex, and we did some experiments looking at prefrontal hippocampal communication. When you think of the hippocampus, you think of spatial navigation. When you think of the prefrontal cortex, you think of working memory, executive control. And so Matt Jones did a task incorporating spatial working memory, looking at place cells in the hippocampus, and then, in the prefrontal cortex, you tend to think about working memory cells, delay cells holding information in mind. But of course, a better way of thinking about it, working memory, is memory that is actually put to use in some task-dependent fashion. So it's the use of memory rather than the maintenance of memory. And again, I will remind you that one of the observations that we had made was the fact that prefrontal cells can phase lock to the hippocampal theta rhythm, suggesting that they might be listening to activity in the hippocampus. And so a task that Matt Jones, who was a postdoc in my lab, developed and used is shown here. This is a spatial working memory task. Animal starts in one of these two starting arms, comes down, runs down the central arm, and then actually has to make a choice depending on where it started from. In this case, the rule could be a match the sample rule. If you started on this upper side, then you have to go to the same side. Animal then turns around, comes back, and is forced back into one of these arms. So in this direction, the animal chooses. When the animal runs back, we choose. This is a memory demand here, no memory demand here, but otherwise the task is behaviorally symmetric. It's running, it's turning. And so the question was, if we look at the hippocampus and the prefrontal cortex, here in this region of the maze, in these two directions, in this direction, there's a working memory demand. In this direction, there's no working memory demand. Can we see something indicating the presence of working memory functions? Choice, forced. And what we're going to look at is the theta rhythm, for all the reasons I pointed out to you earlier. And we can look at the timing of spikes in the prefrontal cortex, the hippocampus, with respect to the local and remote field potentials, the theta rhythm in the prefrontal cortex and the hippocampus. And the result is actually fairly straightforward, and that is that when the animal is running in the choice direction, in this case, animal's running in the choice direction, there's an increase in the coherence between the theta rhythm, the two theta rhythms in the prefrontal cortex and in the hippocampus. And there's an enhanced phase locking of prefrontal neurons to the hippocampal theta rhythm. So when the animal's making a choice, the prefrontal cortex, cells in the prefrontal cortex are locked to the hippocampal theta rhythm. But beyond that, when the animal is going in the choice direction, but makes an error, and that is fails to effectively make use of working memory, that's actually predicted by the absence of this coherence. The hippocampus is working, the prefrontal cortex is working, but they're not working together, and therefore the animal makes a choice, but it's not driven by the communication of task-dependent memory, working memory to the prefrontal cortex. And this is just indicated here, not only in the phase locking of prefrontal neurons to hippocampal theta rhythm, but in the phase locking of the two oscillations, or the rhythms in the prefrontal cortex and the hippocampus. And that's shown here. If we look at coherence between the hippocampus and the prefrontal cortex across frequencies, what you see is a selective coherence here in the theta band, when the animals are going in the choice direction and they get it right. So the presence of theta band specific coherence is predictive of correct choice in a working memory task. Well, so it suggests, again, there's something about activity in the hippocampus during the theta rhythm that can be used to make simple working memory decisions, going right or going left based upon where you started from. And so Josh Siegel and his graduate student in my lab decided to test this explicitly by using optogenetic approaches to try to effectively introduce a temporal lesion. The idea was, let's run that task, the same task that I showed you before, but let's turn off the hippocampus right in that choice region. So an animal's running up there, it's going to make a choice, and the hippocampus is not there. That was the idea. Now, that was an interesting idea, and Josh actually tried this. He used optogenetic approaches which involve infecting inhibitory interneurons in the hippocampus with channel rhodopsin, which will allow you to drive the activity of these neurons, interneurons here, with very tight temporal precision on the order of milliseconds. In this case, a 10 millisecond pulse gives you 10 milliseconds of spiking activity, which then inhibits the activity of pyramidal cells. So these are the place cells, and they can be inhibited, in this case, around the order of about 25 milliseconds. So what that means is you can shut off cells on the time scale of about a theta rhythm. Actually, even slightly less than that, a fraction of a theta rhythm. So what Josh did is he went in and he tried just inactivating the hippocampus. Now, of course, if you're going to do this, you have to make some decisions. Do you just turn on the interneurons and shut the hippocampus off altogether? Do you perhaps lock the inactivation to the theta rhythm? And if you do that, what phase do you actually choose? So Josh was thinking, well, I should just try these things. So what he did was he used a design where in this task, he had the animal performing the task, and then he would simply inactivate the hippocampus at two different phases. He thought, well, I don't know which phase is the right phase, so let's just try 0 and 180 degrees. We'll try in phase, out of phase, and let's just try it at different parts of the maze. So we'll do the inactivation here, where the animal's going to make the choice, but we also want to know whether or not just applying optogenetic activation screws up the hippocampus. So as a control, let's just apply that inactivation here when the animal's in the starting arms. So two different phases, two different theta phases, and then two different task phases. And then he just ran the task, just randomly introducing, driving, inactivating the hippocampus at two different phases. And what he got was not at all what he expected. Now, the thinking was, based on what I showed you earlier, well, if you shut off the hippocampus here, animals should make working memory errors. So I should be able to impair performance on working memory task by turning off the hippocampus at the right phase, whatever that is. One of those phases is probably more effective in shutting off the hippocampus. What he instead found was he got a double dissociation of task phase and theta phase, which led to an enhancement of performance. They actually got better. But it wasn't like there was a good phase and a bad phase. It wasn't that, the peak, inhibit the peak and the animals get better. Inhibit the trough, the animals get better. No, it required the pairing. And that is that when you inhibited the peak, that is, you stimulated the peak, shut off activity at the peak, when the animals were here in the encoding segment, they got better. If you inhibited the trough in this segment, which we refer to as the retrieval segment, the animals got better. Two different phases, both of which could improve performance, but only when applied at the right behavioral task phase. So getting a double dissociation in general is unusual. Typically it's done through lesioning. You have two areas, maybe the hippocampus, the caudate, and you find out the hippocampus is necessary for spatial tasks, the caudate necessary for non-spatial tasks. But this is a temporal lesion. This is saying this phase is important in retrieval, this phase is important in encoding. Now, what does that even mean? So you shut off activity in one phase, and the animal gets better. You shut off activity in the other phase, the animal gets better. Well, think about it this way. Let's go back to this. Well, let's go back to this illustration of the hippocampal code. So there are two pieces of information the hippocampus has. Where am I and where am I going to go? Now you can think about where am I. That's like encoding information. That's the kind of information that you'd want here in this part of the task. But you can imagine when the hippocampus is running, both pieces of information are being expressed. So when the animal's here, in the theta rhythm, the animal is both getting information about where it is and also information about where it's going to go. So there's both present and future information being expressed in both task phases. But now the way we've constructed the task, if you're here, it doesn't matter where you're going to go next. So if we can shut down the irrelevant channel, so here, if we shut down the prediction channel and then bias activity to only the encoding side, and that is the present state, animals do better. Conversely, here, if we shut down the encoding channel, doesn't matter if you keep track of where you are, there's only one place you could be. The question is, where are you going to go next? So by shutting down the competing channel, we can enhance the impact of the remaining channel. So it's the idea that you have these two pieces of information that are being multiplexed. They're both competing for downstream impact. In this case, we have, you can say we enhanced performance, but we didn't really enhance performance. We just steered performance toward the particular task. But what it points out is that phase, it's not just that I can decode and I can make an argument that there's different information in these different phases. Here, I can show you that there's different information, and it can be directly behaviorally demonstrated. Different phases, different functions, different impact on behavior. Now, that's just the behavioral story. But if you look at the anatomy of the hippocampus, it's quite interesting. So the area that we're recording from in CA1, this is a sort of a diagram of the circuitry of the hippocampus. And CA1 gets information from two pathways. One, this so-called monosynaptic direct pathway from the entorhinal cortex. This is neurons in the layer 3 of the entorhinal cortex project directly into CA1. And then there is this trisynaptic pathway where information comes in from the superficial layer, again, primarily layer 2, through the dentate, CA3, and then into CA1. So there's the direct, the indirect. CA3 is interesting because it has the strong auto-associative recurrent connectivity. And when you get to CA1, not only do you have convergence of two pathways, but these two pathways are both theta modulated, but they're also phase shifted. And that is information from CA3 and the entorhinal cortex come in 180 degrees out of phase. And it just turns out that the information from CA3 arrives during that future predictive component of the CA1 theta cycle. The entorhinal influence comes in at the present state. So you have two different circuits feeding two different phases, communicating two different types of information. And so if you think about this hippocampal circuit is actually designed to combine through two different pathways, present and future state information. It separates it in phase. And now the question is, once you have this very clever code, and you can think about the future predictive code, it's like this, as Lucia was describing. You have this kind of predictive estimator. CA3 is making a good guess about what's going to come up next based upon past experience, and also some kind of internal prior model that's embedded within, presumably, this network. And what it's doing is it's predicting what's going to happen in the immediate future. Now, most of what we do, if we think about our kind of conscious, I don't know whether I'd even call this conscious memory processing. The animal's walking down the arm, and it decides to go left. Does it really think, where did I start from? Oh, I started from that arm over here. I think if I go left, I'll actually end up over here and I'll get a reward. You might think that's kind of like conscious introspective evaluation. But this feels more like it's an automatic processing of experience translated into behavior. What would this more kind of explicit introspective evaluation look like? Well, it would have this flavor of being able to link together not just immediate states, but a series of remote states. You should be able to think back to where you started from. You should be able to follow a path leading to a location of anticipated reward. You should be able to think about what the consequence of that might be and then choose or act upon that. And you might want to be able to think about more than one option. Well, what would happen if I went left? How about if I went right? Evaluating multiple outcomes, choosing the one that actually satisfies the goal. That's more what I would think of as kind of conscious memory evaluation would look like. So, can we actually see that? This is just a summary of the idea that the theta rhythm is the mechanism for capturing immediate, present, future state, that it can be mapped into particular circuits that contribute to those different components, and then a phase multiplexing of past state and future state information. But this state that I was sort of alluding to, this kind of introspective, thoughtful state, where it's not action, but it is introspective evaluation of past and future action. And there is a state that's like that, and we refer to this as the quiet, wakeful state. Typically when animals are engaged in consummatory behavior, satisfying internal self states, grooming, eating, copulating, anything where you don't have to think about what you're doing. You can act, but think about other things. And when animals stop, for instance, tasks like this, at the end of an arm and eat, they switch into this quiet, wakeful state. And as I kind of pointed out to you earlier, that quiet, wakeful state is indicated by the presence of these sharp wave ripple events. It looks a lot like non-REM sleep. Dave Foster, when he ran this experiment where he had an animal run. This is the first time an animal's run on the track, runs from one end to the other, and then it just stops, just sits there a couple of minutes. This is very typical for animals when they're learning new tasks. They do a lot of stopping. And, of course, the conventional wisdom of animal stopping is that's like a slacker rat. It's lazy, it's not learning anything because it's not doing anything. But what Dave found when he looked at activity during this stopping period, where you see these periods in which there appear to be a lot of synchronized activity. This is like 19 cells, and you notice there are these periods where it looks like all of the cells are firing, like a simultaneous burst. But if you expand this in time, what you find here, the local field potential expresses these sharp wave ripple events, and the cells do indeed fire, but you notice here they fire in this kind of sequential order, very reminiscent of what I showed you in non-REM sleep, but in this case, it's a sequential order that goes backward in time. So that was the surprising thing. One, that you have this kind of reactivation during quiet wakefulness, looks like REM, but also it's in time reverse fashion. Now, why would you want to do time reversed reactivation? Well, Dave Foster happened to have done his doctoral work on reinforcement learning. And one problem reinforcement learning is known as the temporal credit assignment problem. And that is how you learn something when you're only given feedback on your performance after you finished, after the fact. It's like trial and error learning. You try lots of stuff, something works. Well, what you want to know is not that it worked. You want to know, what did I do out of all the things I did? What did I do that actually led up to that? So you want to spread credit. When you find a reward, you want to spread credit backward in time to those things that led up to it, those things that you could use subsequently to predict and then generate actions that will lead to it. That's the problem that you want to solve. And it just turns out that computationally, there's an easy way of solving the temporal credit assignment in one shot, and that is when you get to this point, you get reward if you run the state sequence backward in time and then pair that with a reward signal. Let's say a dopamine signal that looks like this. The pairing of this and this gives you this, essentially solving the temporal credit assignment problem in one shot. Well, there's a question, A, does this happen? The way you would need to determine that would be to record in the hippocampus and in the dopaminergic signaling areas in the brain to see whether this happens. And I'll show you the data which we took doing exactly that experiment, showing that indeed there is pairing of reward signaling during this kind of reactivation. But before I get to that point, Where's Francisco? What's our time? 10 minutes? Okay. Sort of part of that little story I told about this kind of conscious introspective evaluation, you need to be able to take a state, arbitrary state, sort of move back into the past, and then run through a series of sequences leading to a goal. Now, this is not like these sharp wave ripple events or the theta sequence events. They're very proximal in time. They're short and they're restricted to this one fires second, this one fires third. So when you sweep it on the tail end of these receptive fields, you get a reverse sequence. I sweep it over here on the positive gradient edge of these fields, I get a forward sequence. And indeed, when Yorubusaki actually, shortly after we published this, did the same experiment, looked at reactivation sequences here at the end, where he found reverse. He looked at them here in the beginning, and he found forward. So, simple model can explain all of these, perhaps not entirely intuitive phenomena with a very simple biophysical model. But if we take this, the idea that the biophysics will allow us to do this forward and reverse sequencing, but how do we actually do this kind of extended remote evaluation? And that kind of extended remote evaluation is what you might want to use if you were doing like prediction and planning. Again, I'm trying to think about future goals. And Dave Foster, when he left the lab, started his own lab, he did this experiment where he had animals searching in an open field, searching for a hidden reward. And when animals would stop, he would look at these reactivation sequences. And what he found is that in an animal doing some kind of search, exploratory search, the replayed sequences were biased in the direction of the goal. They didn't actually plot out paths to the goal. They weren't thinking of exactly what do I need to do, but they were evaluating or exploring the space of possible sequences that could lead to the goal. So this is the idea. These hippocampal sequences, if they're expressed, they don't reflect a behavioral plan. They reflect a behavioral search. They're exploring the space of possibilities. Somebody else is actually choosing which of those plans or sequences actually get executed. So to understand how these sequences might be expressed in a larger context, not just these short tracks, but the kind of task an animal might engage in if it were, in doing kind of naturalistic navigation, large spaces, long sequences. Tom Davidson, a graduate student, Fabian Klusterman, a postdoc in the lab, developed this task. It's a 10-meter long track, and the animal's going to walk along and stop. It's the same track that you saw those original movies. And we can look at activity when the animal stops here. And I kind of pointed to those instances where it looked like there were the decoded sequences jumped around the maze. Well, that's exactly what we're going to be looking at. The animal's going to be walking along the maze, and then it's going to stop. And when it stops, so this is the actual position, running, in this case, walking from about 0.6 meters to the end, 10 meters, and then just stopping. When the animal stops, you see these periods of what appear to be synchronized spiking. This is the average multi-unit, just the total activity. When we expand one of these little windows of total activity, for instance, this one, it looks like this. That's a period of elevated activity lasting about half a second. Silent, active, silent. I'll just point out, this looks a lot like those upstates that I pointed to during slow wave sleep. The difference is, it's not a slow oscillation. It looks like an isolated, discrete upstate. And it's occurring when the animals are stopping, and it's occurring in the hippocampus. And during this quiet, wakeful, up-like state, where you see lots of activity, here you can also see that there are these sharp wave ripple events occurring. But in this case, in an extended upstate, you notice they're not just single ripples, they're multiple ripples. Here I've identified there are 4 ripple events. And if we decode the spiking activity over this 500 milliseconds, we get an extended sequence. So this is the decoded trajectory over this 500 milliseconds. And I'm just going to point out something here. A single sharp wave ripple lasts about 80 milliseconds. This is about 400 milliseconds, 80 to 400 milliseconds. And so this looks like an extended sequence across multiple ripples. That in fact, this mode of activation, what I refer to as ripple bursts, is actually fairly common. A sequence of ripples in which individual ripples are capturing a sequence. and that sequence of sequences gives us an extended sequence. And so this is just illustrating this in a little movie where I'm going to show you the decoding. This is the decoding of that sequence, and here I'll show it to you on the track itself. And one property of this decoded sequence is that, again, it's broken down into smaller chunks. So longer sequences are made up of chained together short sequences. So in this case, it's a sequence running from where the animal is right here. So it runs from here all along the path to a point. Again, this is about a 5 meter long sequence. And you find many such instances of these extended sequences, not just in the forward direction. They can be in the reverse direction. They can start at remote locations, at current locations. And again, when you break down these long sequences, what you find is that they're made up of a series of short sequences, and that those short sequences, so this is the probability of being at a particular position, so this is kind of the strength of decoded sequencing. And so you see the strength, it's not smooth, it actually has this kind of piecewise continuous form, and the peaks occur at the points of ripple events. So you get a burst of ripples, long sequences. And that longer sequences take longer time, and that is there's a fixed time of replay, what I sometimes refer to as the speed of thought. And speed of thought in this case is about, the average speed here is about 8 meters a second. Again, I'll remind you back when I showed you that theta sequence slide, the speed of theta sequences is roughly 8 meters a second. So what it's saying is these replayed sequences are running at the same speed as the theta sequences. It's just that these are like a series of theta sequences chained together. I actually like to refer to this as this is like the perfect run. If an animal expressing theta sequences were actually able to run at 8 meters a second, if it could actually run through that at 8 meters a second, that's sort of what it would look like. Each theta sequence would be kind of optimally juxtaposed, no overlap. If it's running it slowly, there's repeated theta sequence activation, and they kind of overlap. As you speed it up, there's an optimal speed where now the theta sequences perfectly align. If you go faster than that, now you're going too fast. So the optimal speed, 8 meters a second. Oh, the battery, yeah. So that's the speed control here. Speed control is that has limited battery. Oh, just hit you just acknowledge it. It'll still run. Okay, so you got this optimal sequence, same speed as the theta sequences. But I want to go back to this, the idea of learning, reverse replay, temporal credit assignment, that, are these memory sequences actually used for learning, and do they reflect some kind of learning? If they were involved in learning, you would expect them to be paired with associated reward signaling. And again, in planning, you'd want to be thinking ahead, evaluating potential reward. I'm just going to point out here, the open field reactivation does not actually map onto what animals actually do. It's more like a simulation of what they could do. It's more like exploration. So Steve Gompertz, when he was a postdoc in the lab, did these experiments looking at recording at dopaminergic neurons in the VTA and the hippocampus. And of course, dopamine cells sort of rose to prominence with the work of Wolfram Schultz, where he found that dopamine neurons in the macaque conformed to the reward prediction error models of reinforcement learning. And so we're recording in the VTA and the hippocampus. And the question is very simple. We're going to run on that same task. Only now we're going to be looking at dopamine activity in addition to hippocampal activity. And what you find in dopamine cells, you find dopamine cells that have a variety of behavioral correlates that will ramp up as the animal approaches a reward, that will fire at or after the delivery of a reward, and there are other non-dopaminergic cells just fire over the task. So you have these reward-associated neurons. What's interesting is after learning, these reward-associated neurons will show this kind of ramping activity, and that is, remember, this kind of temporal credit assignment problem, the idea of spreading reward backward in time. Well, that's exactly what these dopamine neurons are doing. In fact, they're spreading reward backward in time until they reach the choice point. This is exactly what you would expect with what's referred to as a QTD model of learning. This kind of Q, it's in sort of an action temporal difference error model of learning. That is, the prediction error only matters when you actually have to make a choice. And that's where you see this kind of scaled dopaminergic activity. What happens, not during running the task, but when animals stop? So animals going to stop, we're going to look at hippocampal reactivation, we're going to look at dopamine units, and the first observation is that when there are these hippocampal, this is the response of hippocampal neurons around sharp wave ripple events. We can decode the precise positions within the replay sequences. And so we can ask, do dopamine neurons really know what position is actually being expressed in a replay event? And can they coordinate their spikes with the occurrence of the replay of specific locations? And the answer is yes. The dopaminergic neurons are biased to fire at the time when the hippocampal replay events reach goal locations. So when the replay events reach a goal location, approximately 80 milliseconds later, VTA neuron, dopaminergic neurons will tend to fire. So the replay event itself knows what the hippocampus is replaying, knows where goal locations in that replay event are occurring in, and are biased toward that. But not only that, we can look at reward-associated activity in the context of two tasks. Here, it's just a linear track. There's reward, there's action, but there's no cue, there's no contingent action, there's no choice. As I pointed out to you earlier, in this symmetric task, there was a difference in the way hippocampal information was used by the prefrontal cortex when the animal was choosing and not choosing. Well, it turns out these dopamine neurons have the same property, and that is, if we look at the preference, the reward bias, and that is the fraction of locations that are associated with goals that dopamine neurons tend to fire on. That's just simple. We look at when does a dopamine neuron fire, what are the locations that the hippocampus is decoding at that time, and it just turns out when dopamine cells are firing, they're twice as likely to fire at goal locations when the animal is replaying or running in a working memory task. If it's just running in a linear track task with no choice, there's no additional bias. So somehow the VTA knows the hippocampus is replaying a sequence in a task that involves a choice that leads to a goal, and I know where the goal location is. This suggests in some way that this is not just a passive expression of goal location correlates, but it's an active expression of some kind of goal-directed learning. Now, what would that be? Now, the simple answer would be, it's that reverse replay model. It's temporal credit assignment. So we looked at that and asked, do the dopamine neurons prefer reverse sequences? No. Do they prefer forward sequences? No. It's something strange. I still don't know what it is, but what they prefer is replay events that move away from the animal in either forward or reverse directions. So it's some kind of learning that involves evaluation of egocentric state. It's like, where am I now? Where might I go? And how could reward be used to help learn or select behavioral trajectories? And just to tie in the last one, there's just two slides here. Even though this isn't the sleep part, you could say, if this is a property of reactivation, does this occur during sleep? And the answer is no. The weird thing is, you get the same reactivation events in non-REM sleep as you do during quiet wakefulness, but you're lacking the dopaminergic signaling. Dopaminergic signaling shut off during replay and sleep. That's kind of weird because Karim Ben-Shanain, not long ago, did an experiment pairing dopaminergic stimulation. He stimulated the medial forebrain bundle, which targets the VTA neuron projections into the nucleus accumbens, activated dopamine, contingent upon activity of a place cell. So recorded a place cell. When the animal's asleep, stimulated dopamine neurons every time that place cell went off. Animal wakes up, brings it into the apparatus, and you know what? The animal prefers that location, a location it had never actually experienced any reward in. It literally learned something it had never experienced by pairing dopamine with hippocampal activity during sleep. And that tells you something pretty profound. The brain sure can learn with dopamine during sleep, but for some reason, the normal brain is not actually engaging that. It's not trying to use dopamine necessarily as a learning signal. So what this says is, either there's a non-dopaminergic kind of learning going on during sleep, or there's a very selective engagement of dopamine. Again, think about it in this exploratory sense. The idea that the hippocampus and these replay sequences are exploring lots of possibilities. You don't want to learn about all of those. You want to search, select, and then selectively reinforce. Here, this is a non-selective reinforcement. It's like I already know the answer. I'm reinforcing that location, and that's what you do. In normal sleep, the idea is that you do kind of a broad search that involves some kind of composition of extended sequences from smaller elemental sequences. In the course of that exploration, you can evaluate outcomes and then selectively reinforce potentially different combinations of events in the service of some broader learning, not specific task dependent, but the broader objective of building models of the world. And so that's the idea. You see dopamine during trajectories, sharp wave ripple bursts. An interesting thing I didn't point out here, but that is the dopamine units that actually lock to sharp wave ripple events are the same units that actually show theta phase locking in that task. So when the animal is running down, making that choice, hippocampus phase locked in the prefrontal cortex, there are VTA neurons that are phase locked at the same time. Those are the neurons that seem to preferentially engage in the subsequent reactivation. Again, suggesting that theta contributes not only to the encoding, but capturing of information that contributes to subsequent reactivation. And that there's a difference between sleep, sequence memory replayed during quiet wakefulness, and sleep in terms of reward and learning. And the one slide I didn't actually put up there, which I was going to do at the end, and that is all the people in the lab that contributed to that. Josh Siegel, actually everybody here I realize is now left. It's not present and former. These are all former, but that's a good thing. Josh, who's at Allen Institute, Matt, who's at Bristol, Albert Lee's at Genelia Farm, Diane G, who's at Baylor, Foster, who was at Hopkins but just moved to Berkeley, Fabian Klusman, who's now at University of Leuven, Tom Davidson, who's at UCSF, Dan Bender at UCL, and Steve Gompers, who just took a position at Harvard MGH. Thank you.
Thank you so much. We have time for 2 questions.
Hi, thank you again. When you talked about the hippocampus and prefrontal relationship, how the low gamma, high gamma stuff fits on that model?
Yeah, so low gamma, high gamma. So you're referring to the fact that there's this the inputs into the CA1, which come at different phases, also have associated with them gamma oscillations at different frequencies. So there's a high gamma rhythm, higher frequency gamma rhythm associated with the entorhinal input, a lower frequency gamma rhythm associated with the CA3 input, and because those 2 inputs are actually phase segregated, there's actually a phase gamma rhythm frequency is different at different phases of the theta rhythm. Now, I mean, my opinion of the whole gamma phase, the gamma frequency, the different is I mean, there's been this idea that there are like 2 gamma channels, high gamma, low gamma channel. It's kind of reminiscent of the theta rhythm, which also it comes in different flavors. There's a higher frequency theta oscillation known as type 1 theta, which is associated with locomotion, which is slightly higher in frequency, 10 hertz. There's a lower frequency theta known as type 2 theta. It's more associated with kind of sensory stimulation. That rhythm is cholinergically dependent. So they have slightly different mechanisms, slightly different frequencies. So it's possible. Are there frequency signatures of inputs coming from different sources? Because that's what the 2 types of theta, they're basically theta rhythms that come from slightly different sources. Why are they different frequencies? That's unclear. I think the gamma rhythms, my guess is what you're actually seeing, it's what I was actually referring to earlier, and that is there's a relationship between gamma frequency and strength of drive. Stronger drive, higher frequency. And so I don't think it's got anything to do with necessarily a high or low gamma channel. It's just that under certain conditions, you're going to have a gamma drive that's going to be a stronger entorhinal drive than CA3 drive. Into slightly different rhythms. I believe you could construct tasks where, let's say there's, I'll even throw it out there. You imagine there's sort of impoverished immediate sensor information, but there's enriched predictive information. Animal in a familiar environment, you turn off the lights. My guess is you'll see the future past of sequence. It's just that a sequence itself is not just a series of states. It's like there's states that have different degrees of confidence or certainty. I'm really sure where I am now, but I'm not so sure where I'm going to be in the future. So if you actually looked at and you kind of thought about how do I actually compose or build and execute a model that has that kind of graded uncertainty, it would sort of look like that. And that kind of uncertainty is going to change. I'm more or less confident where I am now, where I might be, depending on, let's say, the internal model that I have. So I think those two different contributions, and like the gamma frequency, could reflect that. Now the other thing, this magnitude drive related to the velocity coding, which is I think an interesting question, velocity is just another way, you think, oh, velocity is just, another measure. But velocity is important because it actually captures information about time. You can use that, the velocity information, to kind of evaluate what is the actual time required to execute this. And so you might use this in tasks that require precise timing, perhaps the kind of motor skill learning, where not only execution of the proper states, but executing at the proper time, that is linking action, state information, might involve kind of precise regulation of gamma oscillation. So I could see there experiments where, again, you fiddle with gamma frequency and it disrupts consistency or accuracy of performance of motor component or action component of some of these behavioral tasks.
All right, I think that's it. Thank you, Matt. Thank you so much.